This video is going to be a part 2 on which matters more. If you have a shooter on a shooting range shooting a bullet down range, which matters more, a crosswind up range or a crosswind down range when it comes to causing a bullet deviation. See my other video for the details, but the gist of it is we have a shooter right here. We're looking down from a bird's eye view. This is all grass that we're looking at right here. Here's the target. Shooter shoots the bullet due east to hit the target. In the first scenario, the bullet encounters a crosswind that blows due north, and that crosswind covers half of the range. That bullet will then follow a parabolic path as it's getting blown off course until it exits that crosswind halfway down the range. Then it travels in a straight line to its final destination at the end of the range. That bullet will be traveling relatively fast right when it exits the barrel because it has not experienced any drag as it's went through the air yet. So it's traveling faster, so it won't be in that crosswind very long. So it will have a small amount of deviation, but that deviation will be geometrically multiplied or magnified as it travels the rest of the way downrange to its final destination. The next scenario is the shooter shoots the bullet towards the target, shooting due east. The bullet encounters no crosswind over the first half of the range, then encounters a crosswind over the second half of the range. But the bullet is now traveling slower because it has experienced drag as that bullet flies through the air. Thus, since it's traveling slower, it will be in that crosswind longer and have more deviation from the crosswind. So if you were to draw this out as a triangle and say connect the hypotenuse from the beginning of the crosswind to the end of the crosswind right here, you could say which matters more, a wide angle carried out over a short distance. That would be a downrange crosswind versus an uprange crosswind, which will have a narrow angle carried out over a long distance. In the part 1 video, I showed that when the wind is blowing over 1/4 of the range, a crosswind uprange matters quite a bit more. But then I realized that if the crosswind blows over half of the range, that might give me a different result. So I should probably reshoot this video and see what happens when the wind blows over half of the range instead of 1/4 of the range. Okay, these notes are a little out of order, but as usual, I don't really care enough to fix them. I'm just going to use them anyways. So first off here, the formula we need is time squared equals distance. This is the time that the bullet is in the crosswind. This time squared comes from the full formula, 1/2 AT squared equals distance. But I am genericizing all of these equations for 2 reasons. First off, it gives very easy numbers with which to work. Thus, I only have to use, say, 1 or 2 or 3. And I don't have to actually use the real parameters of the bullet, such as like a 7.62 or a 308 or 270 or something, where I actually have to get the dimensions of the bullet, calculate the drag on the front of the bullet as it flies through the air and slows down, calculate the drag on the side of the bullet as the crosswind blows it off course, get the mass of the bullet, then get the acceleration of the bullet. So anyways, that's a lot of math, but most importantly, because I'm not afraid of the math, I like long, complicated math problems. Most importantly, if I use these equations and plug in the actual real numbers from a bullet, then it might look like that these equations and this math only works for that specific bullet. But because we're using the same bullet in this thought experiment, this will be the same bullet that encounters the same crosswind, either uprange or downrange. I can just genericize all these numbers, make the numbers very small, and then it's easier to see, I think, that this math and these equations will apply for any bullet. Okay, so anyways, we got here. What I'm going to do here is I have to turn the x-axis right here where the bullet goes down range. I can't actually use distance, I have to use time. And this is the problem that took me months to figure out. But I can actually turn the distance into time because we can just pretend that the bullet has a constant velocity. This actually will not change the trajectory. In reality, the bullet is slowing down from drag as it goes down range. But once that bullet exits the crosswind, time no longer matters. We just use distance and the slope to find out its final destination. So that bullet could take an hour to travel over the rest of the range, or it could just take a few microseconds. Either way, time doesn't matter. So I can just say time and distance are equal. I can use this equation here, distance over times velocity, distance equals velocity times time. Let's just say velocity is 1, Therefore, those three dots mean therefore, distance equals time. Make those a little darker right there. Now that I have time here, now I can actually find out, now I can use for how long that bullet is in the air to get the lateral deviation, to find out how much it'll be blown off course, and to get its slope, its final slope here as it heads towards its final destination. And this will be the final destination of the bullet, as opposed to someone from the movie Final Destination, where say they could be downrange doing some sort of maintenance and they're in the wrong place at the wrong time, and then they reach their final destination. But that's if you're watching the Final Destination movie. Okay, so I can genericize all the numbers. I can turn distance into time. I'm going to just say that 1 unit right here will be the first half of the range, 1 unit for the second half of the range, so a total of 2 units for the whole length of the range. So scenario 1 is the bullet is fired, travels east towards the target, but encounters a crosswind uprange that crosswind covers the first half of the range. That bullet will travel for a unit of time of 1 until it gets to the halfway down the range. It will cover a distance in the x direction of 1 also, and it will be blown off course, a distance in the y direction of 1. So we end up with a point here, 1, 1. When the bullet exits the crosswind, it will have a certain slope here, and I'll show how to calculate that slope. And the bullet will hit downrange here at 0.3 for its relative deviation. And I'll show how I got all these numbers. As for what else I have here, I just said must use time to get the deviation. Distance is of no use for the x direction right there. I use distance and slope to get the final destination of the bullet, and I'm genericizing all the numbers. So on to the next page here. I'm using the physics equation, 1/2 at squared equals distance. So that time means the longer that the bullet is in that crosswind, the more it will be pushed off course. I can genericize this to just time squared equals distance. The bullet is in the air for 1 unit of time, travels in the x direction for a distance of 1. I take 1 squared for time, that gives me 1. So the bullet will be at 0.11 when it gets halfway down the range. My other 2 equations I use are y minus y1 divided by x minus x1 to give you slope. And then I also need to take the derivative of my formula, which is time squared, to get that slope. Derivative of t squared is just 2t. Again, you can see my other video, the part 1 of the video on how that works. And I've done several other videos on the basics of calc and trig and everything else, so you can see those if you want. Okay, so the slope is 2t, so that means we need to plug in a unit of 1 for our time. 2 times 1 is 2, thus our slope is 2 at that point. Notice that the longer that the bullet is in that crosswind, the steeper that slope will get as the bullet travels up that parabolic path. So we use our slope formula of y minus y1 divided by x minus x1 equals slope. Our slope will be 2 at that point right there. Go ahead and solve for y. We end up with y equals 3, so the bullet will land downrange with a relative deviation of 3. That number by itself means nothing, so we need to use the bullet that went through a crosswind downrange to find out what its deviation is, to see which one matters more. And I think that's it here, so I'm going to show the next page now. I'm going to somewhat arbitrarily give this bullet downrange of average velocity. That's velocity sub average. So it'll be 0.75. So the bullet downrange here will have an average velocity of 75% compared to the average velocity of the bullet uprange. Remember, we're dealing with average velocities here because that bullet is slowing the entire time it travels downrange. But if we have that average velocity there, then we can use that to determine how much time that bullet has spent in the crosswind. So distance over time is velocity, therefore distance over velocity is time. The bullet is traveling at 75% of its velocity compared to uprange. I picked 75% of the velocity for a reason, and that was because I did a previous video on finding the distance to a shooter. And in that video, I did some calculations for the 7.62 that's shot by an AK-47. And from my calculations and everything I read, when a bullet loses about 20% of its muzzle velocity, so it's only traveling at about 80% of its muzzle velocity, that will put it beyond its typical effective range. So in this scenario here, if a bullet only has 75% of its muzzle velocity, or in this case, 75% of its average velocity when compared to the uprange bullet, that means it's lost 25% of its muzzle velocity. And like I said, from what I've read in my calculations, that would typically put the bullet outside of its maximum effective range. Of course, that would be maximum effective range for a single target, such as a human-sized target. If you're just doing harassment interdiction fire, then yeah, you could be way out there and, you know, shooting all over the place just to harass people. But at any rate, I'm sticking with the 75% here. So anyways, distance over velocity is time. That means 1 over 0.75 gives you 1.33. That is the time that the bullet will be in the crosswind. The reason I showed this here is I'm just showing the significance or the logic on why you can just take the inverse of velocity to get your time. So now we know the bullet is traveling through that crosswind downrange, and it's spending 1 1/3 more amount of time in that crosswind downrange compared to uprange. Now we can take t squared equals the time squared equals the final deviation of bullet 2 in the y direction. And so we just square 1.33, that gives us 1.8. That means the bullet has flown off course a unit of 1.8 compared to 3 from when the bullet went through a crosswind uprange. I forgot to write that here. There you go. So you can see that even if we're dealing with a pretty slow bullet that's lost 25% of its muzzle velocity, crosswind uprange still matters more. I've got some more calculations on the next page I'll show. Now we can find out when the bullet deviation from a crosswind downrange will equal the bullet deviation from a crosswind uprange. Let's take 1 over velocity equals time, then time squared equals distance or deviation in the y direction. Since 1 over v equals t and t squared equals distance, I can just plug 1 over v into t and then square it, and I get distance in the y direction or deviation in the y direction. 1 over v squared equals 3, because 3 is our deviation from the uprange crosswind. So if 1 over v squared equals 3, that means 1 over 3 equals v squared. Velocity equals 0.58 or 60%. That means that the bullet downrange needs to be traveling at about 60% of the average velocity compared to uprange, so that the crosswind downrange will equal the same deviation as the crosswind uprange. And next page. Just a random thought here. I was wondering, where will the straight path of the bullet intersect the x-axis? Right here. Here's the slope of the bullet. Notice it comes down here and intersects actually in front of the shooter. When I first started doing this and trying to figure this problem out, first off, I just never thought of using calculus. And that's just because I only had one calculus class. And I don't do this for a living, so I just do this for fun. So I was trying to solve this just geometrically, and I was just trying to take this bullet path right here that's the hypotenuse of this triangle, and I was trying to connect it directly to the shooter to where the bullet would land. And it actually gave a decent result. You can see my part 1 of this video to show that it still gives a similar result. But there are 2 problems with that approximation of connecting the hypotenuse to the shooter. And that's if you want to be mathematically perfect, and I think that's just one of the satisfying things in life, when you can do something mathematically perfect instead of just estimating. 2 problems with that is that first off, the hypotenuse here doesn't actually connect to the shooter. So if you make the hypotenuse connect to the shooter, it's just not accurate. Secondly, by connecting that hypotenuse to the shooter, you have now decreased your slope, which means you have decreased the amount of bullet deviation from an uprange crosswind. All right, enough with that tangent there. Where will the straight path of the bullet intersect the x-axis, which means where y will equal 0 and the slope m will equal 2. Another way to phrase this is that you could say a straight line, or the bullet passes through point 11 right here, has a slope of 2. What will x equal when y equals 0? Just use our slope formula, y minus y1 divided by x minus x1 equals slope. We can use actually this 0.11, we can plug that in for either y1 and x1 or just y and x, doesn't matter as long as you're consistent. And let's go ahead and solve for x, and we will get 1/2. So that means this point right here of the hypotenuse of this triangle will connect at 1/2 point, which will be 1/4 of the range. And that is because point 1 is at the halfway mark of the range. So if you divide that in half, then you get 1/4 of the range. My drawing's not exactly accurate there, but close enough.